work through that. Come in, come in.
Okay, so last presentation, all about the JVM. This presentation, all about the Java language, and specifically about patterns in Java. Now, that's not like pattern matching using the matcher class and the pattern class and things like that. I did put a slide about that in this presentation when I first created it, and I did this as a webinar a while ago, and it was quite funny because my first slide had, you know, pattern matching and using matcher and pattern, and I actually saw some people drop off the webinar when they saw that slide. And if they waited just like 5 seconds longer, I had the next bit which said, we're not going to talk about this. So we're not going to talk about just regular pattern matching type regular expression things. This is about type patterns. Okay, so the first thing is that patterns in programming languages have been around really since the beginning of programming languages. You can go all the way back to the 1960s. If you look at languages like Haskell, or anybody use awk? Okay, good. There's people as old as me here. So this is something that's been around for a long time. But what do we mean in this context as a pattern? A pattern consists of two things in this respect. So the first is what we call a match predicate. And that's essentially saying that we have a pattern that we're looking at, and we need to determine whether that predicate is matched. So it's a Boolean evaluation. Something we look at and say, is it true or is it false? So that's our match predicate. Are we matching that thing? And then associated with that, we have some pattern variables. And they can be 0 or more pattern variables. Those variables will be conditionally extracted if we match the target. So it's rather sort of formal definition, but you'll understand what I'm talking about as we go through and we see these in action. So this is what we mean by pattern. Two things, predicate and variables. Now there are different types of patterns. So first of these is a constant pattern, where we're matching on a constant value. This is already in use in the switch statement. So if you look at a switch statement, you do case 1, case 2, you're matching against a constant value 1, and then you do something with it. But obviously, because there is a constant value, there is no variable associated with it. More interesting are type patterns, because then you're matching against a type within the Java language. And that's most of what we're going to be talking about here. But there are some others. There is a deconstruction pattern, which is sort of an extension of the type pattern, because you match against the type, but then we also extract some information from it. And we'll see some good examples of that later on. Then we have the var pattern type, which is where we use type inference to map to a specific type. And that's related to the feature that was introduced in JDK 10, local variable type inference. Now we have var in Java, so we don't have to provide an explicit type. We let the compiler infer it for us, and we can use that in our patterns. And then the last one that we're going to deal with here is the any pattern, represented by an underscore. And this is where we match against anything, but we bind to nothing. This is useful in some places. And again, we'll come to this more towards the end, and you'll see how we can use this. There is actually one more pattern type which we don't use at the moment, which is a method pattern, but since we don't use it, I haven't put it in here. Right, so before we get to pattern matching, there are a couple of things that were introduced in Java in the last few, well, really, like last few years, which are very relevant and we need to have a little bit of a talk about. First of those is switch expressions. So switch has been in Java right from the very beginning. The reason it was included in Java is because much of the basic syntax of Java is based on C. Reason being that lots of people knew how to program in C, so why give them a whole new set of syntax to learn to move to Java? Give them a familiar feel in terms of the way we use braces, in terms of the way we use keywords and things like that. So switch was one of the things that came from C. Who here has used a switch statement? Yes, everybody. Okay. Now, switches are really good. They're very useful. They do have some problems. They can be error prone because when you create a set of cases that you need to match against, you put some code that you want to do associated with those cases, and then you have to remember to put a break after that. Otherwise, the way that the statement works, and this is the definition of it, is you will drop through into the next set of cases. So you've all used switch. How many of you have forgotten at some point to put a break statement in? Yes, most people. And that can cause problems that are difficult to find because you look at the result and you go, I cannot possibly have got to that statement because I should have come through that bit there. And then eventually you go, oh, I forgot to put the break in, and I drop through into that bit. Also, there's some other things like scope of local variables, which can be less than intuitive. Right, let's look at the switch statement in a very common usage that we have, which is where we're going to switch on one variable and assign a value to a different variable. Switch is really just like a multi-line if then else. So what we're saying is switch on day, and then for each day we want to assign a value to number of letters. So we have this, switch on day, case Monday, Friday, Sunday, assign number of letters to be 6, great. Otherwise we drop through and we get number of letters to be 7. The other thing about this is that, again, in terms of error proneness, is that we have to remember to assign a value in each of those set of cases to number of letters. If we forget to do that, and we're using an instance field rather than a local variable, the compiler will let us do that. And it will just say, right, well, number of letters is going to be 0 if you don't assign a value to it, because that's the default. We can catch it with a local variable because it has to be assigned, but okay. So this is less than ideal for reliable Java coding. To solve that, in JDK 12, we introduced the switch expression. Now, rather than a statement which simply executes a set of instructions, we now have an expression which will execute a set of instructions and generate a return value that we can assign to something. This is really good because it says that now we can solve one of those problems by having one assignment of number of letters to be the result of the switch expression. And then the compiler can test and make sure that for every set of cases, we have either a return value explicitly or we throw an exception. And that way we can catch things at compile time rather than runtime. Always better for that. Now, if you look at this code, it's a lot shorter than the code on the previous slide. And there's a couple of reasons for that. One is that the developers of this particular feature, they looked around and they discovered this miracle where you could use a comma-separated list. Rather than having each case on a separate line, let's put them all on one line and separate them with commas. It took us 25 years to figure that out. Wow. But anyway, so now we have case Monday, comma Friday, comma Sunday, and then we borrowed some of the syntax from the Lambda expression. We use the arrow operator. On the right-hand side of the arrow operator is the value that will be returned from the switch expression, or in the case of the default, the exception that will be thrown. The great thing about this is that we've shortened the code, made it much more concise, but we haven't lost any of the readability. We can still see exactly what's going on, and we've eliminated a lot of the potential problems. Don't have to worry about break, only assign the value once, compiler can check that. So this is much, much better. Switch expressions must be complete or exhaustive, and we'll come back to why this is important with pattern matching later on. The other thing we need to talk about before we get to patterns is algebraic data types in Java. Right, first thing there. We do this a lot in Java, which is we create simple data classes. Example here, point. Point consists of two values which are doubles, x and y. To do that, we need to create a class called point. We then have two instance fields, private final double x, double y. We need a constructor. So we have public point, we pass in the value of double x and double y, we assign those values to the instance fields, and then because they are private, we need accessor methods to those fields. So we have a method called x and a method called y that returns the values of those fields. That is 14 lines of code to create a tuple. Now, if you look at JDK 8, for example, there are 4,500 public classes in JDK 8. None of them is tuple. Why? I thought this was, a bad thing. And I spoke to Brian Gertz about this, who's the chief architect for the OpenJDK. And I said, why do we not have a tuple class? And he said, if I give you a tuple class, you'll want a triple class, and then you'll want a quadruple class. And where do you stop? And it's like, makes sense. So they came up with a better solution to simplifying a simple data class. Records, introduced in JDK 14. Now, records are simply a special form of class, in the same way that enumeration is a special form of class. Here, what we're doing is we're saying, okay, we'll use this new keyword, record, to indicate that we have record. And then to define that record, we will use the same syntax that we have for the constructor. And we'll say the name of the record is point, and it has two values, double x and double y. All of the rest of the code that we saw on the previous slide, those 14 lines of code, is generated automatically by the compiler. We still have the empty braces because it is a class, but we don't have to define the instance fields, we don't have to define the constructor, we don't have to define the accessor methods. All of that's handled for us. So we go 14 lines to 1 line. Very good. Records, being a special form of class, can do other things. So we could have a generic record. Anything of type T can store an object of type T, and we can store whatever we want in there. Similarly, because it is a special form of class, we can add other things to it, but not everything that we can add to it in terms of a normal class can be added to a record. So circle has a declaration which has a single value that we store in it called the radius. We can't add any other instance fields unless they're the record declaration. So they have to be in the record declaration. You can't add an instance field like Z, for example, but you can add static instance fields. So pi with a fixed value, that's quite okay. And you can add other methods like area to calculate the area of your circle. Java is an object-oriented programming language. So we have inheritance. And we create a simple type hierarchy like this. So we have shape as our superclass. We've got 3 subclasses, triangle, square, and pentagon. The problem with this is that we don't have much control over who can subclass a particular class. So we can declare shape, we can declare triangle, square, and pentagon. But before, if anybody wanted to subclass shape, they could just go and say, I'm going to extend shape, and off they went. The only way we could prevent that was by making shape final. And in that case, nobody could subclass it. So it's all or nothing. That can be problematic. So in JDK 15, we introduced the idea of sealed classes. Sealed classes says that we have now some other modifiers that we can use. So we can declare a class called shape. We'll add the modifier sealed to indicate it's a sealed class. Also applies to interfaces. Turns out an interface is actually still a class. So we have a sealed class called shape, and then we have a permits clause which says that the 3 classes that can subclass shape are triangle, square, and pentagon. That then sets up a type hierarchy which is fixed and sealed. If somebody comes along and says, I like that class shape, I'm going to subclass it and create a new one called circle, then the compiler won't let you. It'll say class is not allowed to extend sealed class shape, not listed in the permits clause. So it becomes very simple, and you can catch errors like that. Why this is important will become clear later on. So sealed class is inheritance. It's also important to understand this. So all of the subclasses of our sealed class must specify explicitly their inheritance capabilities. And there are three ways of doing that. The first is that you can continue to have a sealed subclass. So we can say public sealed class triangle permits further equilateral and isosceles versions of triangle, and it extends shape. So that's fine. The second thing we could do is to prevent any further subclassing. So it's make it final. And then the third thing we can do is we can effectively unseal it. And we do that by using this strange looking keyword, non-sealed, which has a hyphen in it. Now, it has to be said that the amount of discussion that went on about whether we should introduce hyphenated keywords into Java was a lot. But it was decided that it was, if we wanted to be able to extend the language, in the future with lots of different things, that having hyphenated keywords in Java was going to be a good idea. So this is our first hyphenated keyword. Something that's also very important about this is that it's not a reserved word in the same way that, like, public is a reserved word, class is a reserved word. Non-sealed is what's called a contextual keyword, meaning that it only works as a keyword if it's in a particular place, and that particular place is as a modifier to a class definition. There's a good reason for that, because I could write this bit of code. I could say, let me create an integer value called non and an integer value called sealed. And then I could say sealed equals non-sealed. But of course, in this case, that's actually saying that the hyphen there is not a hyphenated keyword, it's actually a minus operator. I'm subtracting sealed from non and assigning the value to sealed. I always like to see how far you can push the syntax in Java. That's a good example. Right, so now we move on to pattern matching. The first situation is related to instance of. So in Java, being object-oriented, we have the concept polymorphism. Polymorphism says that when we have an object, we can view that object as any of the types that it actually is. And because of inheritance, we can have the concrete type that it is, any of its superclasses up to object, and any of the interfaces that that class implements or any of its superclasses implements. So you can view that object as any of those types. That's polymorphism. But because we can do that, there are times when we need to determine if a reference that we have is of a specific type. And we do this, using instance of. So we're used to this. We say if obj instance of string. So we've got our reference and we need to know, is it a string? If it is, and we want to use it as a string, then we're forced to always perform an explicit cast with an assignment. And technically you think to yourself, why? I mean, if we've said if obj instance of string and it's true, then surely we know that obj is a string. So why don't we just allow you to treat it as a string and call the length method on obj, because the compiler knows that it's passed that test, so it should work. But that's not how Java works. So we are forced to do an explicit cast with an assignment. Pattern matching for instance of solves that problem, sort of. And this was introduced in JDK 14. So now what we're saying is if obj instance of string. Now remember I said that a pattern consists of a match predicate and pattern variables. In this case, the match predicate, something that we evaluate true or false, is obj instance of string, because either it is a string or it's not a string. That evaluates true or false, and then we have a pattern variable s, which, depending on whether we have a string or not, will be assigned to the value of obj. If we do have a string, then in the true branch of the if statement, we can use s as a string without doing that explicit assignment and cast, and simply reference s.length. In the false branch or the else branch, then we know that it's not a string, so we couldn't reference s. So the scope only works in the true branch. Now we can be a little bit more clever than that, and we can add another test. Or we could say if obj instance of string s and s.length is greater than 0. This will work because we know that the AND operator in Java, we always evaluate the left-hand side, and only if it evaluates to true do we evaluate the right-hand side. So if the left-hand side evaluates to true, we do have a string, and therefore s has scope which is valid, and we can then call the length method on it and test it against 0. If we tried to use OR, that wouldn't work, because again, we know the OR operator, we always evaluate the left-hand side, and only if it evaluates to false do we evaluate the right-hand side. In which case, if it evaluates to false, we don't have a string, scope of s is not going to be valid, so we can't call the length method on it. Now, scoping of pattern variables for instance of is something that we need to talk about a bit, because it can be a little bit more complicated. We could invert the test, and we can say if not O instance of string and give it a pattern variable s. So that means that if we don't have a string, then we return from this method. What that means is that effectively the true branch of that if statement is the rest of the method, meaning that the scope of s will be valid for the rest of the method. We can print out the length, we could have several hundred lines of code, and then we can still print out the length. So scoping for binding variables, the pattern variables that we use, is different to local variables. It uses what's called flow scoping. If you look at the way that scoping works for local variables, the Java definition says that the scope of a local variable runs from where it's declared until the end of the block in which it's declared. And whether that's a for loop, a block of code, a method, that's the scope that it gets. The other thing that's important for local variables is that they are subject to definite assignment. You have to give a local variable a value, otherwise the compiler will complain and it won't compile your code. Now, for binding variables, they are also subject to definite assignment, but that actually defines the scope of them. So the scope of a binding variable is all the places where it would have a definite assignment. And think about the example there. If obj instance of string, the true branch of that if statement is where that has definite assignment. So that's the scope of the S. If you invert the test, where it has definite assignment is the rest of the method in which it's being used. So this is what's called flow scoping. But it's not the same as local variables. We can do something like this. We can say if O instance of integer, so that's our predicate, and then give it a variable which is called num. But then we can also have an else if O instance of float, and then we can reuse num as the variable, and we can reuse it again if we have a long. We couldn't do that if we're using local variables, because we would say, oh, num has already been used. But because of flow scoping, you can reuse the variable name in all three of those situations. And that's really good because it just simplifies some of our code by not having to think of, random variable names for that situation. Okay, pattern matching for instance of puzzle. Right, so here's a piece of code. Object S equals new object. So I'm assigning a new object instance to S. And then I say if S instance of string S. So S instance of string is my predicate, and then I'm trying to use S as my pattern variable. And if it is a string, then it'll print out the length of the string. If it isn't, it will print out no string. So let's have a little show of hands. Who thinks that this code will compile? Oh, who thinks this code will not compile? Okay, same number of people. Who thinks this code will both compile and not compile? Because that's the answer. Strangely, there is a quantum superposition of this particular piece of code. So if you put this into your IDE, so you fire up your IntelliJ and you type this code in, you will get an error. You will be told that this is not going to work. The compiler will say that you've already used s as a variable, and so you can't reuse it. It's a local variable. You can't use it as a pattern variable. However, if you use JShell, it will work. Now, I haven't tried this on 23 yet. I should do because it's coming out next week, but it still works on 22 and it will work. So you can do object s equals new object. It says, yep, okay, that's fine. And then you say if s instance of string s and blah, 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 and it will say no string. It will work quite happily. Nobody has yet been able to explain to me why this works, because as far as I understand, JShell just sits on top of the Java compiler. But there must be more to it than that. And even some people from Oracle who've looked at that and gone, no, that shouldn't work. Don't know. But it's interesting. Right. Pattern matching for switch. So we talked about the switch statement and the switch expression. And if you look at switch statements, they're fairly limited in terms of what you can switch on. You can switch on an integral value, so a number, or you can switch on strings or on enumerations. What we've now done is expand that so that you can also switch on a type pattern. Here's an example. So we have our method called type tester, takes an object reference, and then we switch on O. And then we have cases for different types. First one, interestingly, is we can do case null. Now, again, what we've got there is a match predicate, which is case null, so we're matching against null. But this is a sort of example of both a type pattern and a constant pattern, because we have a constant type. So in the case of null, there is no variable, so there isn't any point in having a variable associated with it. Null is null is null, so we can simply print out null type. For string, case string is our pattern predicate, and then we have the pattern variable s. We can print out the value of s on the right-hand side. Similarly, if we have a color, give it C, and we can print out the RGB value of that. Now, we'll come back to this later on, but for now, the switch in terms of types can't work on primitives. So primitives, yes, it can. I know. Yeah, I'm going to come back to that for JDK. It's actually in JDK 23, I believe, or is it 22? It's 22 or 23. I will come back to it at the end because now you can. But in this point, we're talking about that. So at this point, you can't switch on a primitive, but you can switch on an array of primitives because that is technically a type in Java. So null, like I said, is special. This is kind of interesting because I've had this conversation with various people about null, and null is one of those really kind of interesting types in Java. So you can have a case null, and that can be used in all switch statements and expressions. If you don't include it, the compiler will include it for you, and that's to maintain backwards compatibility. So backwards compatibility, we don't want you to have to go and add a case null for every single switch statement you've ever used. So the compiler will, if you're using it in a more modern version of Java, will insert it for you. So effectively what happens is if you compile this piece of code where you've got string, color, int array, and default, the compiler will insert a case null, which will throw a null pointer exception. So it behaves in exactly the same way that it did before, but it's allowing for the insertion of a null case if you want to. Now, the interesting thing as well is that because we have this now comma-separated list ability in the switch, we can also say that we want to handle a null reference in the same way that we do a default, where we have got something other than the types that we've already listed. And so we can say, okay, print out bad input, and we can avoid the null pointer exception. I think that's a really good thing. So that kind of tidies up code quite nicely. Because before, we would often have to put an explicit if statement outside of the switch to catch the null before we passed it in. Completeness. So I mentioned this when we talked about switch expression. And so for pattern switch statements and all switch expressions, they have to be exhaustive. Let's look at this example. So we have type tester, and in this case, we have a switch that only has two cases, one for string and one for integer. What happens if we pass in a float or a color or any other type? Well, you could argue that because switch is like a multi-line if then else, because there is no case for either of those things, you just ignore it and you move on to whatever is below that. But the designers of this said, well, that's going to leave too many possibilities for error. So what we're going to insist on is that all switches have to be complete in terms of types, meaning that you have to address every single possible type that could be passed to that. If you pass an object reference, there's an infinite number of types that could be passed to that method. So if you wanted to make it complete, you would have to have an infinite number of cases, unless you use default, because you're effectively saying if it's not a string, not an integer, then everything else is dealt with by default. That doesn't mean that every switch, even if it's complete, has to have a default in it. How can I say that? Well, we can combine the idea of sealed classes with our switch. Sealed classes means that we have a sealed type hierarchy. And we can do this. We could say, okay, now we've got a type tester which takes a shape, and we switch on the shape and we say case triangle, case square, case pentagon, and case shape. That covers all possible types in that hierarchy. There are no other types that can exist in that hierarchy, so we do not need a default. It is complete. Now you might say, well, hang on, what about isosceles and equilateral? But remember, those are subclasses of triangle, so they're caught by the triangle class, triangle case. So that will work. It is still complete. Guarded patterns. Okay, so this is where things get a little bit more interesting. In earlier versions of Java, before JDK 19, they used the same syntax that we saw in the instanceof operator. So they said if case triangle t and t.area is greater than 25. So we're adding what's called a guard to the pattern matching of the type. So we're saying if we've got a triangle, we know we have a triangle, so we'll also add a test to say, is the area of that triangle greater than 25? If it is, we print out it's a big triangle. We also have a case for triangle on its own, so if it's not greater than 25, we'll do it's a small triangle. In JDK 19, they decided that they would do away with the double ampersand, the AND operator, and they would replace it with when, making it more readable, I guess. So we have case triangle t when t.area is greater than 25. I personally don't think this was a great idea. You will see why in a moment. So where when is important. Let's create some code. So we'll have a public sealed abstract class called interrogator, and it's going to permit 5 subtypes: who, what, where, when, and why. We're also going to have a class called when, which is our subtype of interrogator, which extends interrogator, and it's going to have a method called when. Anybody see where I'm going with this? Right. So then we can have a method called test question. It takes an interrogator. We will switch on question, and then we'll have a set of cases. So we'll have case what with a pattern variable called what, and that will print out what. Same for where, pattern variable where, and print out where, why, and we'll print out why, and then default how, because they can't possibly do that. And then we're going to create 2 local methods called where and why, which then allows us to do this. We can have case who, what, when, where, why. Remember that case who is the pattern predicate. So that's saying we're matching on type who. The pattern variable is what. The when is acting as a guard to then say that we're going to test using where, because where returns a Boolean, so we can use that as a test. And then if that is true, we will execute the method called why. And then to be really silly, we can do case when, when.when, when. And like I say, this is where things get a little bit complicated because you have to think about this and you have to break it down and say, right, so the capital W when is the type that we're matching against, so that's our predicate. The first when with a lowercase w is the pattern variable name. The second lowercase w when is the guard. So we're not using double ampersand, we're using when as a contextual keyword. And then the third lowercase when is the reference to the pattern variable that we're going to call the when method on to test whether we've got true or false. And if it is true, we will call the local method, also called when, with a lowercase w. I do not recommend writing code like this.
Could you tell me the operator?
I suppose
When again or what something what
that would be why at the end. So yes, that's where things get a little bit sort of crazy. Yeah, okay, I'll come back to this a little bit later on. Pattern dominance is also something that's very important. So we could reorder the cases that we have for our sealed class. But if we put the shape as the first one, then the problem we're going to have is that triangle, square, and pentagon are all subclasses of shape. So shape will always match everything and it won't ever get to triangle, square, or pentagon. So the code becomes unreachable. Now the compiler will reject that. It will simply say, no, you can't do that because shape is a superclass. It makes all the rest of the code invalid. And so there's no point in compiling that code. But you also need to be a little bit careful because if you use a guard, you also need to be careful about the order because if you do case triangle T on its own, that will again match any triangle and you will never get to the case where you've got a guard to test the areas greater than 25. Helpfully, the compiler will reject that for you as well. Matching instance of and records. So let's combine the ability to test a type with a record. We'll use the record that we had before, simple point, double x, double y. Now what we could do is something like this, calculating the length of the hypotenuse using a single point to represent the point on a triangle. Now we can say if O instance of point P to test whether we have a type which is the record point. If it is, we can then call the p.x method on the reference p.y method to get the values of x and y, and then we can do the sum of the squares, square root, to get the length of the hypotenuse. Which is good, but we can do better. This is where we come into record patterns introduced in JDK 19. And this is an example of a deconstruction pattern. So it's a combination of the type pattern where you're matching against the record, but you're also doing a deconstruction at the same time. And that simplifies things because now, rather than simply giving the name of the record, you give the record declaration. O instance of point double x double y, and then the variables that we've got there in terms of the record contents, double x and double y, we can reference those because the compiler will deconstruct the point record and give us access to those variables automatically. We don't have to call the accessor methods explicitly. So now we can reference x and y without having to call those methods. One of the interesting things about this is that when you use a record deconstruction pattern like this, you have to give it the right name of the record, obviously, so it has to be called point, but you don't have to use the same variable names for the fields in that record. So you can call x, xx, and y, yy. It doesn't matter. So you can use whichever variable names you like, so long as the signature matches in that you've got two doubles. Where did that go? Is it still on there?
it pops here.
I'm still sharing.
Oh no.
see, if I was back in the UK, I'd say we need to put another 50p in the meter. We run out of electricity. Just
Instance of point double x double y and x equal and y equal.
yes, you could put a guard on it. Yes. Yes, you can definitely put a guard on it. What you can't do, I haven't got it up there. What you can't do, because they did allow this to start with, but you can't have if O instance of point double x double y and then give a variable name for the record. So you couldn't have O instance of point double x double y p and then refer to p. So a named record. You can't do that. They did do it originally, but then they ran into the problem, which is where if you try and call your record when, and I did this, call your record when, and then you use the pattern variable when, it cannot resolve, it cannot parse the syntax of the when you use a guarded pattern on a record pattern with a variable name. It just it doesn't work. Okay, so let's see. Yeah, so like I say, so you can have a record as a deconstruction pattern. Yeah, so you don't need to do that. Now, the bit that I was going to then talk about is that you can compose patterns. So essentially, what you can do is you can say, okay, so if I have a case where I've got point and x and y, I could extend that and I could say, okay, let me create another record called color point, which has a point and a color as the things that I store in it. And then you can put that into your pattern predicate and say, okay, so you've got case color point, point P, color C. And obviously you can reference the values in P by calling the methods on it. And then also compose that so you can end up with the idea of having case color point and then having the record decomposed within that. So you have point X, Y, and then color C. So you can actually extend it out and make it longer. And that way you can decompose multiple records to gain access to the records within records. So that's all good. But the problem with that, ended the meeting. The problem with that is that it can get very confusing because you end up with, if you've got, let's say, 3 or 4 levels of records, then you can end up with record within record within record, and it gets, especially if you only want to access one particular element of one of those sub-records. So the answer to that is to use this idea of an unnamed pattern. So just go through here so I can remember to make it right. Yeah, so this is a new JEP, which is unnamed pattern variables. And the idea is that you can match against the signature, so you know that the variables that you've got are important, but any that you don't want to use, rather than have them called out explicitly with the type and a variable name, you simply use a single underscore to show that there is something there, but you don't care what it is. And then only the things that you want to reference, you give a type and a variable name. And that way it becomes cleaner in terms of what you're looking at, and you can identify the things that you actually want to get access to. And that's a fairly new thing because that was JEP 443, which was in JDK 21. And then the other one thing that I was going to talk about, which is what we came back to earlier, is the idea of unnamed. You can use these in, unnamed pattern variables. You can also use them in case with, so if you had case string, and you would normally give it S and use S on the other side of the arrow operator, you could, if you don't want to use the variable, you can simply use an underscore to ignore that. But the other thing is, which is quite important, is JDK 23, which we're getting next week. That's going to have primitive types in patterns, meaning that now you can do X instance of int. And so you can actually have the primitive type used, and you can also use that in a switch as well. So you could have switch on some type, and then have case int I and use that. So you can have primitives as well as full types in there. That does get a little bit more complicated because you can end up with some situations where you've got to be very careful about the promotion of the values in numeric types, because obviously you've got int, short, byte, double, and then so you've got to be careful about how you do that. The best thing to do is to read the JEP for that, which is 455, because it goes through a lot of detail about how you need to identify which values fit into which things, so that you don't end up with some rather odd cases. Yeah. So I'm going to kind of wrap it up there. In conclusion then, so pattern matching is a very powerful set of language constructs. It does certainly make a number of tasks a lot simpler. We can see that by making things easier with switch expressions, using types in those, instance of, now we can use type variables as well, things like that. Leads to less boilerplate code, more declarative code, that kind of thing. And there are actually some interesting things because they're talking about potential for more optimization of code. So it's not just syntactic sugar to avoid having the boilerplate code. There are actually opportunities to do more performance and optimization of these things. I would expect to see more of these features delivered. So we're getting the idea of was it primitive types in patterns next week in JDK 23. There's probably going to be other things that will happen in later versions. I know there was one proposal for having arrays as a deconstruction pattern that was going to go into an earlier version, but they've kind of put that on the shelf for now, but that may come back at a later point. So yeah, so that is pattern matching in Java. There we go. I apologize for the last few slides without slides. Okay, any questions?
One, supposing you are doing, sorry, you are doing a case small int, case int, and you have an integer object as an input. Does it match or not?
Yes, now that's where things get complicated because they're two different things. So you need to be careful because this is where you need to read the JEP, because if you pass in an integer object, so the wrapper class as an object, but you only have a case for an int, I believe, I haven't tested it, I believe it will do unboxing. So it will unbox it, so it's a deconstruction pattern in effect. It will unbox it and provide the int value, which will then be matched on the case. But if you have an integer case, so you could have case integer and case int, then it would depend on what you pass in as to whether it matches the integer object or whether it matches an int. I think. I have to think about that one because I'm not totally sure that would work. Because could you pass in a reference? No, I don't. I'm not gonna. No, I'm not gonna. I'm not gonna ask. I have to look at that one.
Yeah, because if it does the unboxing, what's the point of having the primitive, the case int? Is the integer object always match? I don't know.
Yes. Yeah, I think I'd have to test that one to be definitive about that. I may be wrong in that.
And the reverse. Oh, no, it's not the reverse.
That